Okay. So, you guys know your calculator can do a least squares regression line. You also know that you can linearize nonlinear data. And I had given you questions out of this book last year. Yeah, there was a scan and the questions were out of this book. Abby gets that Thursday, Wednesday? I think it's Wednesday. Sometime this week. Um, so the equation to do the least squares regression line by hand, was that in the video last week? And remember that the regression line is y hat, or predicted y, a plus bx. The a plus bx, it doesn't really matter which one. It's just easier to do it in that order when you're linearizing nonlinear, to put it back. Okay, your answers in this will be an a plus bx form. When you do it on the IB test, you're just going to use your calculator. If you give it an mx plus b, I don't care. They won't care. Okay. IB tends to be not fussy on the it doesn't matter details. Okay. If there's three correct ways to do it, you can pick whichever one of the three. For the sake of this, I don't really care what you write on the test, but if it's multiple choice, which some of them will be, it's going to be a plus bx form. You should be able to rearrange that even if you do the other one on your calculator. Um, so yes, you notice that formula is a pain in the butt if they don't give it to you. You will never use that formula unless they give you all the values. But back in the old days when you had to do that by hand, do you remember how hard the correlation formula was? And yes, you would have SX and SY doing that, but those are a pain to calculate by hand too. You got to figure out each one's distance from the mean, each value, square them, add them all together, divide by n minus 1, square root it for x and y. And then correlation, I can't remember what it was. No, correlation uses both. I think it multiplies each one's x times each one's y. You probably want to use the table method that we taught in Carnegie, where you actually, the stats unit in Carnegie was one of the best ones I've ever taught out of. Yeah, about the only thing I liked out of that book. There were a couple of things, there were a couple other activities I'm like, I like this one activity. There were like four or five that I liked in the integrated one book. Four or five lessons, that's it. But the stats unit was actually very good. And what they do is you make a table, you've got x, you've got x minus x bar, you square it, you add them all together, and you could then take that squared column and multiply them and add them. I think you multiply the x, the deviations in x squared and deviations in y squared, and then divide for correlation. But it'd be a very big pain in the butt to calculate by hand. And yes, they used to do it. Okay, so what is the meaning of R? Correlation coefficient, it means what?
From to so it's just
To a line. The true meaning of correlation is only linear. Okay? They will put one on so in your Inspire can put it on for nonlinear, and it'll put R squareds on. The true meaning of R is only for linear. Okay? So the R value probably comes from the, if you remember, we logged axes to make them linear last year. Um, that's where your R is coming from, I believe. R squared has another way of calculating it, but it is the same as literally squaring the R value. Okay? There's an alternative way to calculate it, which I think is why it actually works on some of the other ones. Okay? They might just be square rooting R squared when they give you an R value. Remember, negative R's mean negative slope. Positive R's mean positive slope. Close to 1 or negative 1 is good. Close to 0 is horrible. Zero point 0.5 is actually pretty bad. R squared. Do you guys know that meaning? No. It is the percent of Y that can be predicted by X. R squared. Percent of Y, and you will be required to put them in the context of the problem. One of my favorite ones from chapter 14 in this book, you can get the percentage of a baby's intelligence that could be predicted by the amount they cry. About 23%, which isn't very much, but 23% of a baby's intelligence can be predicted by how much they cry. Dumber.
Yeah, that makes sense.
Okay.
It should not be rewarding.
Like neglect.
That will also lead to them being dumber. So notice it's only a 23% predictor, but that's not zero. Okay. So you see how I put that into the context of the problem? That is what you guys have to learn how to do for everything, but specifically for stats. They will really harp on it for stats. But there's almost always a point at the end of any of the longer problems for telling your answer, what does it mean in the context of the problem? Okay. Um, they're usually relatively easy points, yes. If you remember to do them and you're clear. It will not be as easy in some of the stats ones. Okay. Some of these will be challenging to interpret correctly. Okay, they call this the least squares regression line. Okay. So it literally means my points are here, here, and here. The distance here is 3 to the predicted. Predicted is the line. So that's 9 squares, right? 9, 9, 36. The idea behind the least squares regression line is you are using the line that will give you the least squares. Okay? And there's the nice formula is there to given to you to use. Your calculator does it, but that is the theory behind what it is doing. It is minimizing the square of what's called the deviation from the line for all the points. Mm-hmm. The line? The line here is diagonal. The deviation, no, it has to be vertical. So this one is the deviation for x value 3. It's not the shortest distance. It's the vertical deviation. Because this is the value for 3 versus the predicted for 3. That makes sense? Which is actually way easier to calculate than the shortest distance. That makes sense about r squared. You don't really need to use the complicated r squared formula. R squared is called the coefficient of determination.
Ooh, that's tough.
Okay. R is called the correlation coefficient, r squared coefficient of determination.
No, that's like an pound. I don't know why it's coefficient determination. Oh,
So,
I'll make it coefficient.
facts about least squares regression. The distinction between an explanatory and response variable is essential in regression. It does not matter in correlation, but it does in regression. When you switch y and x, it matters. You will still get the same correlation, but you will not get the same regression line. Okay? So this is data for the expanding universe. You guys kind of know that the universe is expanding, right? Yeah,
You taking a course on?
she's in physics. Yeah, that's part of it. So notice what happens when you switch y and x. You get different lines. It doesn't mean that they can't ever be switched, but you do not get the same results. Um, Fact 2. There's a close relationship between correlation and the slope because R is part of this correlation. Okay? Calculation. The worse the correlation, usually the flatter the slope. Okay? Fact 3, this one's important. The least squares regression line always passes through the point x bar, y bar. That's involved in the a value or the y-intercept. Okay?
That's where I'm not sick. Just Joe's.
Good, because I don't want to get sick. I don't want you to be sick. You got too much work to do.
No key.
You're like, yeah. So, the fourth one, I don't remember. Fact 4. Correlation describes the strength of the straight line relationship. R squared is the fraction of variation of y that can be explained by x by the least squares regression line, y on x. No.
Is that a fixed thing?
No, that's a logic puzzle. That's from Bill.
Wait, Mr. Schwartzman, did you ever had to like lay down and put in some cardboard? Just off topic.
Have I ever had to install carpet?
Yeah.
I've helped install carpet before.
Is it not
Like
visible
this.
when you like
Use knee pads.
I did and then it hurt so awkward.
Oh, yeah. So go to Harbor Freight, spend like $18 on some gel knee pads, and they really, really help.
Because like how one was bad.
Okay, so anyways, we need to keep going. So you remember the Sanchez family and their gas thing? That was an earlier example from last week, right? So we can see that their R is 0.9953 and their R squared is 99.06. So 99.06% of the variation in gas consumed per day can be predicted by the heating degree days.
That's really good.
That's really good. The Hubble one that I just showed you has an R squared of 61.5. So 61.5% of, I need to look back. The velocity can be explained by the distance. That makes sense? The velocity of expansion. Okay, do you guys know what residuals are?
No.
Distance from the line.
That one's each individual distance from the regression line. The person that didn't do this at integrated one remembers.
They did it with this.
Oh, okay. You guys did get there. That's good. And it's like Izzy did it with me, Devin did it with me, Rowan did it with Mr. Klein.
Ooh, and then I get in.
So basically, this is observed minus predicted is residual. Half the residuals will be 0. Or negative, not 0. If you add up all the residuals, it should be 0, which is why you square them. Okay? So,
Observed y minus y.
or y minus y hat for each value. Each value has a residual. Okay? So each x that has an actual value also has a residual. If you've made regressions and you go back and list, you'll see stat.resid in your calculator. That is a list of the residuals. It generates it for you. It will generate it automatically. You can put it in a list. If you put it in one of the columns and hit stat.resid, it will list out all the residuals. Okay. Very useful. Okay. You guys saw this data before, right? So we have child 19 as an outlier. Child 18 is what we call an influential observation.
Because it's not quite an outlier.
It's an outlier in the x direction.
Oh,
So influential observation means outlier in the x direction. It will drag the line towards it massively.
influential one.
Influential observation. I'm not sure if I spelled that right. I'm not sure if this is a C or a T.
It's a T.
It's a T. Okay. So if we're looking at this, we get an R score, an R value for this data of negative 0.640. I mean, it's not great, but that's not that bad. R squared, 40% of the later score on an intelligence test can be predicted by when they spoke their first words. That's not that bad. It's not great. If we take out observation 18, which not speaking till 40 months, yeah, it's like 3.5. It's like 42 months. That probably means they have some sort of developmental disability, right? So we take out that kid. We just remove them from the data. Um, we get an R squared of only 11%.
Wait, that makes the R worse?
Yes.
Because the data.
The data's being dragged to that and it looks linear when it's not very linear. Okay. Influential observations. You make a scatter plot here with absolutely no pattern in it. And then you put one out here. You will get a relatively decent line. Because this drags everything towards it because its X is so much different. Okay. You'll get even though this was basically no correlation, you put one observation way out on X and you will get something of some significance. Okay. Residual plots. A residual plot is a plot of all the residuals. You take your X coordinate from your points, you graph X versus residual. Okay? I will show you how to make a residual plot in a second. If the residual plot has a pattern, any pattern that is not just randomness, linear was not the right choice. Okay? Do you see a pattern in this one? The variation is getting bigger, right? As X gets bigger. Um, that means there's something there, and I don't know what type of. The curved one I can say was probably quadratic. This one I should have used a quadratic regression on, most likely. This? Very, no. No, you do not try to match. Generally, don't try to match it to the pattern. You'd want to look at the original data and look for what shape it is. A lot of the curved ones are powers or quadratics, sometimes exponentials. Um, this basically is probably going like this with our data. It's getting more spread out, and it might not fit regression. There might not be a regression model at all for it. Okay. To do a residual plot, I'm going to put in a few random points. I haven't done one in a while, but I think I still know how to do this. Put in, 5 points in your calculator. Doesn't matter what they are. We don't have to all get the same one. So I've put in some random points. I'm going to make a data and statistics graph. I really didn't care what I labeled these. So I've made my regression. You don't know how to make a linear regression?
Oh, no.
It's like, you don't know how to make a linear regression. I fail you from pre-calc. I go back and change your grades.
It's not a wild thing.
So, menu. Plot type. Is it plot type? No.
General.
Oh, analyze residuals. Show residual plot. Do I have a pattern in mind?
Yes.
No.
Oh, you mean your residuals? Oh,
In my residual plot.
I didn't- the-
Does everybody get the show residuals? Yeah, like I said, it's been a while, but I like the Inspire because it's in menu. I just went through the menus until I found residuals. Yes. You don't want the squares is going to make that drawing like we had on our thing. Yeah. And that's not particularly helpful. Everybody got that? Able to see residuals? Now we get to go ahead to cautions about correlation and regression. Yes, but that's one. We essentially did that last year, so we're not doing it again. Cautions about correlation and regression. The least squares regression line is not resistant. What does resistant mean to?
It's, if it's not resistant, then it's affected by outliers.
Yes. Okay. Outliers will have a major effect. You saw the one effect of that influential observation. Outliers, we call them if it's in the y direction. The x is in the middle, but it's in the y direction. We call that an outlier. If it's in the x direction, we will call it an influential observation. Does that make sense? Okay. Do you guys know what interpolation versus extrapolation is?
Yes. So interpolation is like making a prediction within the data that you have, and extrapolation is making a data that's like outside of the data that you.
Mm-hmm. Is the extrapolation ever useful?
Yes, it's just not always accurate.
Okay, when I say mild, I would be talking about predicting, if you've got data from the last 100 years, predicting 5 years into the future, probably reasonable. Predicting 100 years into the future, probably not. You got data from the last 10 years, predicting next year or the year after, probably reasonable. Predicting 5 to 10 years out, and sometimes you have to predict 5 to 10 years out, right? So, one of my favorite extrapolation examples. In the late 90s, they posted signs at Glacier National Park. These glaciers will be gone by 2020. It's 2025, they're still there. Okay. Why was their extrapolation so bad?
Assume that it's. Just gonna. Just more.
They assumed that the recent trends would continue exactly the same. With, mhm. And at the time in the 90s, they called it global warming. They changed it to climate change because they realized it wasn't exactly just warming. They discovered more about it. They realized their extrapolation examples weren't, that things were changing. Are those glaciers smaller? Absolutely. They're not gone. Okay. So they, it's important to understand that yes, the actual trend that we're predicting has continued, but not nearly as strongly as they thought. Okay. So extrapolation, sometimes if you're running a business, you might need to extrapolate into the future to make, oh, we can't just build a factory when we realize we need it. We need to plan that 5 years out or something. Um, at least. So there's some level of extrapolation that you have to do. But extrapolation leads to funny results, like, oh, guess we better take those signs down. I haven't been there, so I'm not sure if there's just like pillars or if they put up new signs or
Like, what?
I'm sure it doesn't, I'm sure they didn't put up new signs that make them look as dumb. They might have put up signs about how much they've shrunk or something. That
But right over the other one.
so a lurking variable. This is really important. This is really important outside of math class. This is the number one cause, probably, of miss um misdiagnoses and things. And
Yeah.
incorrect interpretations of data. A lurking variable is a variable that is not your explanatory or response variable, but has a major influence on those relationships.
Dun, dun, dun. I really hope I didn't have one of those sleep. Or-
Yeah, I hope so too. They won't kill you for it in it. I really wish you guys would have had stats before you started the DP program. Because you kind of need stats for biology. Did you guys already do chi-square in biology?
Yeah.
Do you have any clue how that works?
Yeah.
It might be on your actual exam, but we will go through chi-square in February. But it would have made so much of a difference had you already known chi-square when you're trying to interpret it in biology. So hopefully for the future we'll get there. Discrimination in medical treatment. Studies show that men who complain about chest pain are more likely to get detailed tests and aggressive treatment, such as bypass surgery, than women with similar complaints. Is this association between gender and treatment due to discrimination? The answer is actually no. It sounds like it. In most cases, though, women are 10 to 15 years older before they complain about these. So a man complains about this at 60, the woman's 75. Which one are you more likely to do aggressive treatment on?
Younger.
The 60-year-old, he's more likely to be able to handle it.
And
And so the data, without that lurking variable of age of when these symptoms happen, makes it look like discrimination. Okay? And I think there was one where did I do the C-sections example with you guys already?
uh,
Where and I'm like, and it might actually be male doctors are just way more prone to doing this, but they did not give enough detail in there. They did not. It was um of yeah. How many deliveries did these doctors do? Was the one a difficult birth expert? Like, yeah, you don't go see this doctor unless you're going to have a difficult birth and you're expecting to probably need a C-section. And so a lot of there's lurking variables show up. This is my favorite example. A study of housing, or one of them, study of housing conditions in the city of Hull, England measured the large number of variables. Two variables were to measure the overcrowding and the measure of lack of indoor toilets. And if you look at these two individually, do you see a pattern?
Yes.
You see, yes, there's pretty good regression there, right? If you
But
look at them together, there's like nothing.
wait, no, can you just like put the line like right in between them? So
You'd probably get something right almost flat. If you're including all the points, you'd get something about like that. Um, as seen by the R value of 0.14. If you separate them, you get these two R values. They're separated on the percentage of public housing. In districts with lots of public housing and districts without, there is strong correlation between the measure of overcrowding and the lack of indoor toilets. I'm not sure how they measured those two things, but okay. When you get a very bad R like this 0.14, that means the slope of your regression line is probably not actually flat. It's probably more like is close to zero, though. The closer your slope is to zero, the worse your regression. Okay. So, predicting enrollment. This is something colleges have to do because they need to figure out how many professors they need to hire, right? So, the mathematics department at a large university must plan for the number of sections of instructors required in elementary courses. The department hopes that the number of students in these courses can be predicted by the number of first-year students. That would make sense, doesn't it? The table below contains data for several years. The explanatory variable X is the number of first-year students. The response variable Y is the number of students who enroll in elementary math courses. Then we get this regression with an R squared of 0.694. Seems fine, right?
no. No, it just seems low for 30.
Oh,
It seems a little low. We see this weird trend kind of in the middle here, right? There is these points that are above are all clustered together. That's kind of weird. So we're looking at the residual plot. What we're going to see next is they're going to take the residual plot and put them in order by years.
oh,
Something changed between 97 and 98, didn't it? Probably what math is required to graduate. Okay. Between 97 and 98, something changed. Okay. So this was a kind of weird one. There's some lurking variable. We don't know what it is, but they probably should do the regression on 3 years because that old data is now meaningless. Okay. Little bit of a strange thing, but I mean, hopefully the department has a clue what changed, but
hmm.
um many regression or correlation studies work with averages or other means that combine information from many individuals. You should note that this carefully and resist the temptation to apply those results of such studies to individuals. Okay? There's a lot of generalizations. You've heard, how bad generalizing can be, right? Well, generalizing is actually a good thing, except when you apply general standards and try to make it fit individuals. Okay? A lot of generalities are there for a reason. They generally apply. But there's a lot of individual variation, even with pretty strong generalities and averages. Okay. Okay, causation versus correlation.
Oh, the Nicolas Cage thing, that sort of.
Yes.
Yeah.
Yeah, you can go on the internet. There's also a strong correlation between global temperature and number of pirates. Pirates. I can find that at the end. Drowning deaths in pools between number of Nicolas Cage movies. I'll find this. It's it's in it's in my integrated one slideshow.
Wasn't it really one?
I made everybody watch it that first year because none of the rest of you guys had ever had that. And I knew that integrated 2 and algebra 2 had gone through without ever learning that. So, there are some strong examples of causation. Um, there's two causations, there's two common response, and there's two confounding. Do you know what confounding is in here? Confounding means it's too hard to tell. Okay. So, maybe I'll just pull up that slideshow here.
Thank you. Or what's the story possible is.
There it is.
Oh, yeah, I'm not gonna show you some. So I kind of did this one song, majority of the last year. It's the Black Song Express. But I probably sing it too.
This is a good one. I like this one. Aggregate comic book sales and computer science doctorates awarded. That actually might be that might have some causation in it. Injuries related to falling televisions and undergraduate student enrollments. That also might have some level of causation. That one, I'm not sure on that one. Yeah. But the falling TVs, people moving into dorms. The more people move into dorms, the more injuries related to falling TVs, probably.
Oh, wait, some people.
Um, causation, there must be a link related outside of just a correlation. Common response, they both have the same cause, but one does not cause the other. And confounding, it's not clear whether it's cause and effect or other variables are involved. This is common response. Correlation between ice cream sales and sunburn. That is the sunburn and ice cream sales do not cause each other. But hot sunny days do tend to increase both. Okay, that's a great common response example. Okay, back to our book.
Oh, that was the same case.
Nicolas Cage. Oh, this one is good. Autism and organic food sales. Individuals diagnosed with autism, organic food sales. There is probably
Oh my God, that is gnarly.
that one treatment for autism is eating healthier. So there's probably a little bit there.
I am looking at both foods and getting really upset. Have you seen that one movie that he saves the guy from killing himself?
So
That's a lot of reals.
there's more, I mean, the big part is more people are being diagnosed and organic food is gaining in popularity. But organic food is not causing more autism. Autism diagnoses might have a slight effect on organic food sales, but it's probably it's mostly unrelated. Um, I was like, but yes, I do know people that have treated things like that with healthier diet. And it healthier diet makes a big difference for some people.
Serious.
Yeah.
That, I did not know that.
Healthier diet makes a big difference with a lot of, it makes a big difference with intelligence. Like you should plan on eating healthy when you take your IB exams.
Interesting. I'm gonna think back over those chocolate milk things.
I was like,
If it's good enough for him,
so this is the Nicolas Cage one.
with the autism.
Yes. Um, okay, so two of these are causation, two are common response, and two are confounding.
Can we get a guess?
Yep.
Okay.
Two are causation, two are common response, two are confounding.
Yeah, I think number three is causation. That's one they cause each other, right?
Mm-hmm.
Guys, we agree with that?
Mhm.
Three causation.
So
Okay.
you're saying this?
Yeah, and I think one correlation.
Correlation isn't an option.
Oh, wait, sorry.
Confounding. There's two of each.
Wait, and then what was the third one? Uh, common response. Oh, they both have something that causes them. It's like,
Mm-hmm. That's not mentioned in. So you guys think this?
and I think the other causation is number six, the number of years of the educational worker has. Oh, wait. No, I think that's, guys' thoughts.
It's just.
Confounding is there might be some causation, but there's also potentially lurking variables.
Oh, number five. This comes down.
These all are strong correlations. Every one of them.
Monthly flow, monthly rate return, stop. Oh, common response. Yes, that's.
I think so, because there could be other factors influencing returns in stock.
I think one
serves.
Yeah, okay.
And then you guys think two is confounding?
Wait, no, but that one actually. Yeah, that one makes sense, guys, but we should think one of our causations. I feel like number six probably isn't that causing, I'm not gonna lie.
Do you think that's confirmed?
Yeah, I think that might be. Yeah, I think that's confounding, because I feel like that there were like some majors in college where like you like working and you go to school and you don't. The opposite. Yeah, and then.
Correct answers are in red.
Okay.
Oh.
Yes.
That's all that matters.
As your high school senior's SAT score does not cause your first year college GPA. They are a common response to intelligence and work ethic. Okay? Intelligence probably being the big one there. But your SAT score does not cause anything. It's caused by it might cause so there might be a little bit of causation in oh, you did well on your SAT score, you got into a hard college and your GPA is lower. Because you're going to Stanford instead of Idaho State. And thus you're actually I've heard Stanford just only gives A's mostly.
I wanna get a.
And they're also very you only get in there if you're super high good student, and then they were having too many complaints about my student's not a B student. My student doesn't get C's. Well, they're at Stanford now. That's they're in the top 5% of students everywhere, and they're average top 5%.
But I would have these, right, though, I mean, give them the grade we get, but I also think like a lot of the kids there.
I think it's this what we were giving as a C at Stanford would be an A at University of Utah. And so they started, oh, I guess everybody's just kind of getting A's because they're doing what would be considered A work at so many other colleges. They do matter. They do matter for getting into graduate school, which is a big thing for they do matter for a job. Yeah, they will come like when I was interviewing without experience, they did look at GPA. When once you have 10 years of experience, nobody cares. When you don't have experience, they care how you did in college. Now, they'll probably take, oh, you went to Stanford and you got a 2.8 versus you went to ISU and got a 3.5, we'll take the Stanford. Okay. But you went to Stanford, got a 2.8 versus the kid that got a 3.9 at Stanford, they're taking the kid that got a 3.9 in most cases. Okay, there's always other factors. Does that make sense for those?
Wherever.
Okay. Does smoking cause lung cancer?
Technically.
Technically, we do not have enough. We're generally willing to accept it, but we do not have enough evidence. In order to establish causation, you must have an experiment. We have never done an experiment that's long enough on humans. No, because in order to be an experiment, you must randomize the groups. That's coming after break. So we're going to take a group of, well, we need to randomly select them from Americans. We can't pick from Alturas. For example, let's take the Alturas High School students. We're going to randomly divide half of you are in the smoker group. You must smoke until you die. One pack a day. Um, the rest of you are never allowed to smoke anything ever. And you're not allowed to hang out with smokers, drive in a car with someone that's smoking. You can't hang out with them while they're smoking. Uh-huh. So, do you understand why this is something we can't do? The first of all, dividing you into you've been chosen to be part of the smoker group because you can't just take volunteers. That's not true experimentation. We'll get to that after break. That's chapter 5. But we are willing to accept it because the association is very strong across all countries that have smoking. Association is consistent. That's where it's across countries, across the world, across time. Yes, absolutely. Higher doses are associated with stronger response. People that smoke 2 packs a day have a lot more than people that smoke an occasional cigarette or cigars on occasion. The alleged cause precedes the effect by a predictable time. Smoking response in men, lung cancer rates went up about 30 years after smoking became popular in men. Smoking became popular in women like 20 years later, and lung cancer rates went up 20 years later for women. And it has been done in experiments with rats. Okay. Do we have true causation? No. Do we have something close enough that we're willing to accept it? Yes. That makes sense? that is your final lesson